Hello everyone, my name is Dariusz Sosnowski. I also work at NVIDIA, and as mentioned before I get the mic, I also love and live and breathe Flow API. And today I wanted to talk to you about how to look inside what happens in the hardware offloaded rules. So what are existing capabilities of Flow API, some of them existing from the beginning, which allow you to see what happens into the hardware. So just giving another brief intro to Flow API and also expanding on what Alexander has said. So we have Flow Rule API is the basic object of this API, where we have a pattern and actions, what we match on, and what we do. So basically, application calling RT-flow create instructs the PMD to configure the hardware to do some specific actions on some specific packets. On top of that, flow rules have additional parameters. In the API, they're called attributes. So for example, in this diagram, we see that in the box on the left, we have a group 0 on ingress. Ingress is an attribute specifying that this flow rule will happen when the packet is on the RX path in the NIC. The group is an identifier. It's a 32-bit integer, which we can think of kind of organizing the flow rules in the table. So each flow rule created in group 0 will be put in the same table, and they will be processed. You can think of it processed as a single entity. Inside the group, going inside this left box, we can organize them into priority. So first we'll process the rules in priority 0, then on priority 1. Another types of attributes also available in Flow API are egress, which is like the symmetrical version to the ingress, where we want to apply the traffic on the TX side, and also the transfer, which applies to the traffic when we have a NIC capable of having an embedded switch, for example, in the setup where we have VFs on top of, where we have VFs also on the system. So there are a few types of architectures the applications implement when working with hardware offloads. One of them is the partial hardware offload. In this architecture, hardware offload is responsible for only some parts of the business logic. So in this example, when we receive a packet on the wire, we process it in the ingress flows, and all of the traffic goes to the application. And from the PMD itself, we receive the application receives some information about, for example, what is the type of the packet, does it match some specific 5-tuple and assign some ID. And after forwarding it to the TX queues, we can apply some additional logic, for example, metering. Second type of architecture is the full hardware offload, where we basically, if the NIC is capable, we program the hardware to completely take over the packet processing. So after we got some control plane traffic, and we, let's say, slope of traffic, we receive the TCP handshake, we install the rules, and everything happens inside the NIC. For some applications, this is a target application, what they aim for, because here we reach the goal of completely lowering the CPU requirements of the application, and in some cases also lowering power requirements of the whole solution. So if we take a look at these two approaches, we can think of that in both cases, what happens to the packet is a series of black boxes. So for example, in the partial offload, we don't know what happens in the flow rules on the RX side. We receive the packet with some metadata. We push it to the TX side, and then we don't know what happens to the packet on the egress path. On the full offload case, the situation is even worse for application developers, where after the first TCP handshake, for example, we don't know what happens to the packet at all. So I will present some concepts existing in the Flow API which would help application developers to debug that. So first one would be the count action. So this is one of the possibly earliest Flow API actions available. So how does it work? We can specify the count action directly in the flow rule in the actions array. So after we call RT-flow create, in the hardware there will be now a flow rule with a pattern and an action, and one of which will be count. This represents the object in the hardware which counts packets matching on that rule. Later, the application can query the value in this counter, the number of packets and number of bytes processed by this flow rule using RTFlow Query API. On top of that, the Flow API allows us to create shared counters using the RTFlow Action Create APIs and also their async version, RTFlow Async Create. So the flow is like this. We create first the count itself. We create a rule which has a pointer to this count, possibly many. In this example here, we have 2 flow rules, each pointing to the same hardware counter. And later on, during the lifetime of the application, we can query the counter to see how many packets were hit by the flow rules using this counter. So using this simple action, these simple APIs, we can basically count how many packets were matched against the given 5-tuple or given protocol type or given flow group, or even how many packets were not processed by any flow rules we created. This will be covered more on that later. Another useful in debugging of the applications using the Flow API is the meta item and action. Previously, I mentioned that in the partial hardware offload scenario, the NIC sends some metadata to the NIC. NIC sends some metadata to the application about what happened to the packet. So in RTFlow, let's say that the packet arrives on the RX. There is an ability to assign a 32-bit integer to the packet inside the NIC. So basically, whenever packet traverses all these flow rules, we'll have some kind of metadata assigned to it. So let's say that the packet hits some flow rule, which means that we're matching a pattern and we're executing some actions. There is an action called modify field, normally used to perform address translation or port translation of the packets, but it can also set this 32-bit integer to some specific value. This is now assigned, this now goes to the hardware with the packet, and when reached to the application, the drivers set this metadata value in the mbuf. And this is set in the dynamic field RTFlow dynf metadata. So basically, after RX burst, we have the ability to look up this data set by the NIC. On the TX path, the application also can provide this metadata. So for example, if the application received the packet and already read the headers, we can assign an ID to the packet in the mbuf that, hey, it's a packet from connection number 1024. The hardware does not need to match the 5-tuple anymore. We can just work on the index stored in the metadata. And after the packet mbuf is processed by the PMD, hardware will have access to this 32 metadata bits using RTFlow item of type meta to match that value. So, for example, we can use it to kind of recognize the packet classification. Here comes the example of like assigning the connection ID to the metadata. But also we can mark which flow rules the packet traversed. So in this a bit maybe overcomplicated example, on the left we have group 0 where we first match on VXLAN, where we first try to decide if the packet is tunneled or not. When it's tunneled, we go to group 1. This is the box on the top, where we decapsulate from VXLAN. And then in the group 2, at the end, we want to, depending on whether it's IPv4 or IPv6, perform some actions on the packets. So let's say that the VXLAN packet arrives with the inner headers of ETH IPv4. It's matched for the VXLAN rule, and we go to group 1. Here, we perform the decapsulation, and in the red, we have this action for setting the metadata bit, bit number 1 to 1. This will indicate later in the hardware offloaded pipeline or in the application that, hey, this packet hit that specific flow rule or went through that specific path. So here we decapsulate the VXLAN header, and we match the first box in group 1 saying that it's VXLAN IPv4. And we go to group 2 for IPv4 traffic, where we set another metadata bit indicating that we went through this group. So in the end, after we went through all this sequence of flow rules, we can look at the metadata integer in the application, or even matching the metadata bits in the hardware themselves and counting the matches, we can kind of deduce from that which flow rules were hit by on which flow rules the packet was matching the pattern and which action we executed on it. Another existing concept in the Flow API is the sample action, and also utilizing the update rule API, which Alexander presented on the previous presentation, we can additionally enhance the debug capabilities. So sample action itself, it has two parameters to the hardware. One is the ratio of packets we sample, so we can say that one of each 10 packets will be sampled, or every packet will be sampled, and the actions to take on the sampled packets. So in this example where we have the flow rule with some pattern, we have an action called sample, and this will copy some percentage of packets and execute the RSS on them, so they will go to the application, where application can take a look at these debug packets, let me say, and the original traffic will execute the rest of the actions, in this case jump, so jump moves the processing in the hardware from one group to another, one flow group to another. And using the RT Flow Update API, we can basically take the existing flow tables where we have some group with many flow rules with different patterns and actions, and we can update these rules in place to. So let's say that we want to see. We receive the target hardware receives some weird packets on some given 5 tuple, and we want to look at them in the application to debug them. We can take the flow rule, in this case like the second from above, with pattern 2 and actions 2, update it in place, keep the same actions, and also add an action sample, so that right now hardware on top of what it was doing until now, it will copy the packets to the application to debug. So it's basically, we can think of sample as a feature equivalent to switch mirroring of the ports. In other cases, we can add the count, so we can simply count the packets hitting these flow rules, and basically just replace these actions with any other capabilities. We can set the meta to have this ID available to the application to identify the wrong packets, and so on. The last functionality in the group is the group miss actions. So, as I described in the beginning, when we have a group, we have certain priorities. So we have some group, on priority 0 we match full 5 tuple, on priority 0 we match only on IP addresses because we didn't recognize the layer 4 protocol. But now, if there is no match here, the API does not clearly define the behavior for the NICs to conform to. It's vendor dependent. So I believe last year, a new API was added called RTFlow Group Set Miss Actions. So basically what this API takes is it takes the group ID and the list of actions to execute for packets without any matches. So in this example, if we do not recognize the packet at all, we can count them, send them to application, we can sample them, we can do execute any actions on them basically, depending on the hardware support in Flow API, of course. And that's all. One question which we have to you all is basically, when you look at Flow API, what other cases you think are hard to debug, hard to understand how they work, and maybe there would be some new capabilities required to add to Flow API to debug them. And I also think that, yeah, I think that's it. So thank you very much.
So there's a question on Zoom, which I'll just read out here. What mechanism is used in sample action to transfer a particular ratio of packets, and how is it decided which packets should be replicated?
So by the API definition, the sample takes the statistical approach. So it specifies how many packets out of how many packets will be copied. So let's say it specifies that 1 out of 10 packets. So each 10th packet will be copied and sent to the application, basically mirrored. That's like by the API definition.
Any question? Any needs to suggest?
On your example of the group miss action, like what's the difference between that and just adding a priority to rule that matches anything with a set of actions?
That's a very good question. And this can be implemented using another priority with, like, for example, an empty match. But it's also the question of how this is implemented exactly in the hardware, because some hardwares may not accept a flow rule, like explicit flow rule without any match. So we need to match on something, and maybe they provide an ability to, hey, if there's no match, do this. That's one aspect. Another is the performance implications of this implementation. For example, on NVIDIA NICs, setting the group miss actions just sets the pointer from the rule when it didn't hit specifically to these actions. So it didn't go through any default behaviors when we didn't match the packet. Yeah.
But do you really need the API, or could you have just inferred it from, you know, adding a rule? You know, I understand like maybe the hardware implementation is more optimized for this miss case, but could you have just inferred it from a rule that matches any at priority 2? Like, why do you need the API for it?
So one specific reason for this API is that the behavior on the API level is not defined at all. It's regardless if we add a rule which matches any packet or we do not add it, the API does not define what happens when there is no match at all. So the one other purpose of this API is to provide an ability to application to make it explicit in a way and allow drivers to explicitly allow configuring this behavior.
Got a quick question on could you go back to the slide on the set meta, please?
Mm-hmm. Yeah.
In your example, I think your set meta, it's an OR action on the bitmap, is it? Or did I misread that?
It's a set action on the bitmap. So here I made a small mistake on the slides. We have the Flow API has a modify field action, which from the name you can infer that it modifies the packet fields, but it can also modify this meta register, and it can operate on a bit basis. It's like the smallest increment which it can modify is a bit. So we can treat the meta register as a bit mask and set specific bits whenever we hit certain stages of the pipeline in the hardware.
Okay, I need to go back because I use meta like to go set on group 0, for instance, set meta so that you can match it on group 1 or whatever.
Exactly, yeah.
So I use that, but I missed the bitmap. Is that already in?
Modify field API is from 20 to 11, if I recall correctly, so it's already available.
Okay, I missed that. Second question on the meta is, it gets reported in the mbuff in the dynamic section, as you mentioned.
Yes, yeah. Mm-hmm.
What if you have multiple groups setting up the meta? Do you report both, or you only report the last one, or what's the theory there? So
from API perspective, there is a single 32-bit integer, and its life begins when the packet arrives, and its life ends when the packet is received by application or forwarded to the TX or some VF, for example. So you go to group 1, you set some bits, you go to group 2, set some bits, so it operates on the same integer, same register, you can say. Yeah.
Okay, I see. So even if you're even matching on the second one, you would also report it as a final.
Yes. But matching on it, if, for example, bits set in group 1 are not needed, you can always mask them out, because when you match on the metadata, on this meta item, you provide a 32-bit mask, so you can mask out the bits which are not needed.
Sure. But let's say you set it in group 0 and you match it in group 1, and group 1 doesn't care about it anymore. You still need to report it?
Yeah.
Okay. All right. Thank you.
Hi. This is really interesting, and you're really creative. I just went and looked at your 4 different ways of debugging and evaluated it against which drivers support which.
Okay.
And obviously, MLX5 supports all of them, so I'll ignore that from the list. Counting pretty much everybody that supports Flow, all the drivers support count. So Broadcom, CNXK, ENIC, HNS3, Intel NICs, NFP, SFC, everybody does that. The modify field, only MLX5 and NFP support it. The sampling, Broadcom and CNXK and MLX5 support it, so 3 support it. And the flow miss is only an MLX5 thing.
Yeah.
So creative solutions, but we really need to try to get this more widely adopted. And I'm not an expert, obviously, in all those different NICs. I don't know whether that's a question of a driver writer not sitting down and doing it, or the hardware not being able to do it. So we should probably have that discussion with some of those maintainers.
I completely agree. Like one of the purposes of the presentation was also to kind of maybe remind of this existing capabilities, so that we can discuss and talk about adding support in other PMDs, so that applications have more universal experience across the NICs. Yeah, I completely agree with you.
And the other last question was, is there any way to create a packet and inject it into the driver, I suppose through hairpin, but to be able to say, I have this packet, I want to see where it shows up, and maybe use one of these other tools to see where it shows up.
Like simulate how it goes?
Yeah.
I'm not familiar with such a tool. We can always create a packet in an application and send it and see where it will up. But it takes the real application, the real hardware to do so. But like simulation-wise, I'm not familiar with a solution.
And of course, that would allow us to at least start to test RT flow in some way.
Yeah.
Just to emphasize, we are seeing a lot drivers embracing the Flow API, but the Flow API is so rich that it's very difficult to have the same level of support for all drivers, and really we are calling to improve the support level for many drivers.
Related to the Flow API, do you see the synchronous API, simple create, modify, update as your base, they're always going to stay there, or that's going to be deprecated? Because you also have all the asynchronous API, which is a whole set of things, and you got the patterns API, and where do you want to go with that?
Okay, I can answer quickly. There is a simple API, very convenient to use, which is the one we introduced first. But you see some limits when you try to scale very big, like when you reach 1 million rules, for instance, you see some limits. So in this case, you need to use a different set of API, which is asynchronous, using some pre-configuration in template, etc. It's more complex, of course, but it's more powerful. So the idea is to keep both. Dariusz? Yeah. Okay. Okay, one last question.
So final question from the Zoom link. So we have mark, meta, set tag. Do they all do similar work?
So tag is only for like, it's visible only internally in the hardware. So when you set a tag, You can match on it, you can act on it, and it never escapes the hardware. Mark and meta, on the other hand, escape the hardware, so they are visible in the MBOF.